In this lecture, we're going to talk about the independent sample t-test. So recall from the last video that there are two sample tests. So these two sample tests arise in different ways. So one way is where you have two measurements from the same sampling unit. So before, after usually gives rise to such a such a data set. The other is the independent sample t-test, where you have two independent samples and you're taking one measurement on each a unit from each sample. So we talked about how maybe you have a treatment group and a control group, and those are independent of one another. Then you take measurements on each. Let me now give you another example. This is one from some work that I've done. And we'd like to answer this question. So, do high levels of utilitarian engagement with the editorial content of a magazine affect the way people react to the ads? So it's a really age-old question in advertising. That the question is, how does the surrounding context in which you encounter an ad affect the way you react to it? And I think people have known for decades that it must have an effect. So if you're watching a TV program, for example, that's really sad, and you get an ad that comes on and during a sad scene, you're probably going to react to that ad differently than if you're watching a really funny slapstick movie when that exact same ad comes on. So you're primed by the context. You're really sad because of this horrible scene, or you're laughing because it's a really funny movie. That's priming you, and that priming is going to affect the way that you react to the ads that you encounter. All right, so the question is, how do you prove that? So we did some tests, and we were able to measure the utilitarian engagement with the magazine. So what is utilitarian engagement? Utilitarian engagement means that you're getting useful advice and tips from this magazine. It's showing you how to do things the right way, and so forth. Okay, so if you the reader have this perception that I'm going to get real useful advice from reading this magazine, that is going to color the way you respond to the ads in that magazine, versus a magazine where you read it just to kind of escape your the rest of the pressures in your life, or you might read it differently than a magazine that you read to have socially have things to talk about with your friends. All right, so these are all different types of engagement. We're just going to focus on utilitarian engagement. So if you have this sense that this magazine is playing this key role in your life of giving you useful advice and showing you the right way to do things, does that mean that you're going to rate the ads in that magazine higher than somebody who doesn't have that relationship with the magazine, that utilitarian relationship? All right, so here's the experimental design that we're going to study. We've got a control group and a treatment group. So the way to think about this is the control group is a group of people who really don't get turned on in a utilitarian way by this magazine. The treatment group, on the other hand, definitely has this experience, and they'll say, I get good advice and so forth. So this magazine is important to me because it gives me good advice and tips. All right, so the treatment group is utilitarianly engaged, the other one is not. We then expose them to an ad, and we ask them to rate that ad using standard copy testing measures. All right, so O1 is the rating of the ad by those who are utilitarianly engaged with the magazine. O2 is the rating of the ad by those who are not really engaged with the editorial content of the magazine. All right, let's define some symbols. So mu-H, or you could call that the mu treatment, is the mean of the rating of the ad, so the mean of all these O1s, for those who are engaged. Mu L, those are people who have low engagement, so they're not really into the magazine. So mu L is the rating, the mean rating of the ad for those who are not engaged. Okay, we have the sigmas. Sigmas are the standard deviations of these two measures. Now, the central hypothesis that we'd like to test is, does the engagement that a person has with a magazine affect the rating of the ad? All right, so if it has no effect, the rating of the ad for those who have high engagement will be the same as the rating of the ad for those who have low engagement. So the means will be the same. The alternative is that they're not the same. All right, now if you look at this hypothesis, it's immediately problematic. And the reason it's problematic is because it involves two parameters. It's a two-sample test. We got two parameters. We don't know what to do with a hypothesis having two parameters. We know how to handle the sampling distribution of one thing. We really don't understand how to handle the sampling distribution of two things. All right, so what we have to do is a trick. Now we've already done this trick in the paired sample t-test. We're going to just do a slight variation on this. The paired sample test, we took every sampling unit and subtracted, say, the post measure minus the pre-measure to get some differences, and then we did everything on the differences. In this case, we're also going to form a difference. So let's say D is a new parameter, which is just the difference between two parameters, the means of the high versus the means of the low. And so an equivalent test is if we test whether D is equal to 0. So this is equivalent because D is equal to 0 if and only if mu H equals mu L, right? The only way we can get a difference of 0 is if these two things are equal to each other. Likewise, when these things are not equal to each other, then D will not be equal to 0. All right, so having stated the null and alternative and looked at our data, let's now go let's go look at the data that we have. So utilitarian engagement is something that we measure on a 5-point scale, and anybody who has a value that's 3.5 or greater, we're going to say has high engagement. Anybody with an engagement score less than 3.5 we call low. There are 787 people who have high utilitarian engagement, 2,800 who are not so engaged with the magazine. Now, this mean, this is SPSS output, so I know it could be better labeled, but that's SPSS for you. All right, so this mean refers to the mean of the dependent variables. So what is the rating of the ad? So these means are estimating mu sub H and mu sub L. So mu sub H is 4.3-ish, mu sub L is 3.8. Now, sigma sub H is this standard deviation. Sigma sub L is this standard deviation. The standard error of the mean is obtained by just taking the standard error, dividing by root n, as we always do. All right, so what we now have is an estimate of D. Let's call that estimate D hat. Take the difference between the two means, and it's about a half a scale point, 0.5018. Let's go draw a picture. So I'll go over to the sketch pad, and here's what's going on. We can think about, here we go, a sampling distribution. So there's my sampling distribution. This is the distribution of D hat. Now, we're going to do the same thing that we always do. We always assume that the null hypothesis is true. And if the null hypothesis is true, the mean of this distribution is 0. We've come in with an observed difference of 0.50, and the whole problem is going to amount to us finding the area in that tail as we always do. So let's just kind of write this out. What is the probability that we observe a D hat greater than 0.50? And using our central limit theorem, we're going to be able to say this is approximately equal to the chance that we have a Z greater than 0.5 minus 0 divide by the standard error of d hat. All right, so now we need to find the standard error of d hat. How are we going to do that? Well, here's some things that will help us along. So, independent sample t-test for large samples. So, let's say both samples are large. So that's clearly the case here. We have hundreds, even thousands. Kind of the minimum for large is 40-ish. So if we have 40-ish in each sample, which we have here, and the central limit theorem applies. These are the copy testing measures of the dependent variables are measured on 7-point scales, I think. So we don't have any extreme outliers, no problems like that. So the CLT is going to apply. Then the distribution of d hat's approximately normal, and we can use the z distribution to find probabilities. So when I sketch this normal thing, my justification for doing so is this number 1. All right, variation. I'm not going to prove this, but the standard deviation of d hat is going to be the variance of the highs over n. So that's just the, you can think of that as the sampling variance of the sample mean for the highs, plus the sigma squared sub L over n. So this is your sampling variance for the x bar low. We're going to add those two variances up and take the square root. So it's kind of like the Pythagorean theorem. The sum. We're going to add up these two, a squared plus b squared, take the square root to get the other standard deviation. Now, we almost never know sigmas. What we do know are the S's. So these things reported in that table are S's. And if we just substitute in S for sigma, we get the standard error of the difference. One thing to note, S squared sub h over n sub h is the standard error, that standard error of the mean. You've got to square that number. And then this quantity, S squared sub L over n sub L, is exactly what's reported by SPSS for that other mean. You just have to square it, right? Okay, so let's go plug these numbers in. So where did I get 1.3? Here's 1.3 over 787. 1.3 squared over 787. 1.198 squared, well, that's that number squared divided by the sample size. And so there's your standard error of the difference. This is exactly the formula that I wrote. So we've observed a difference of 0.5-ish. So what's the chance you observe a difference greater than that? Well, that's approximately equal to the chance that you have a z greater than this quantity, and you go do the division. 9.72 is your z statistic. Now, if you look in SPSS output, the SPSS output looks like this, and it looks kind of confusing because you have two rows. You'd think you'd only need one row, but it gives you two rows. For now, let's look in the equal variance not assumed row. Okay, now if you look down here, you get a t-statistic reported at 9.72. That's exactly what we computed here. The mean difference was 0.50183, which is exactly what we found earlier. The standard error of the differences is 0.05162. That number should look familiar. That is what we got using this Pythagorean-like formula. It's the number that also goes in the denominator there. And then we go look this up in the z table, and that tails, of course, 0, double 0, you still get 0. All right, so the p-value is about 0, therefore we're going to reject h0 and conclude that engagement affects the copy testing measures after someone's exposed to an ad. Now there's one other thing that we could do. We could alternatively compute a confidence interval. So how do we get a confidence interval? Take our statistic plus or minus 1.96 or 2 times the standard error. So here's the standard error of the statistic, 0.05162, and you get a confidence interval. Notice that's exactly what is reported by SPSS down here, 0.40, 0.60. And we could say, well, since the reference value 0 is not contained in that confidence interval, we're going to reject H0 and come to the same conclusion. Okay, so those are the basic steps. Now, don't get lost. I gave you a lot of details about this. In real life, what you do is you copy the data into SPSS, you run the independent sample t-test, and you come down to this box and you say, aha, the p-value is significant, therefore the means are different. So it's really quite easy to do this in practice, but then all the stuff that happens underneath the hood is substantially more complicated than anything we've done so far in this course, I think. Now the story gets a little bit more complicated. It gets more complicated when you have small samples. I often tell students it's much easier to analyze large samples than small samples. You got to worry about a lot of other stuff when you have a small sample. So one of the things that we worry about is the variances. So if the sample sizes are pretty small, it would be highly desirable for us to be able to assume the variances are equal. So don't do this unless it's plausibly true. So don't assume equal variances because you want to. You have to have some justification for doing so. Now, here's why it's so desirable to make that assumption. Let's go back to this variation formula. So what we're going to do is get to the standard error by taking one variance, dividing by the n, adding the other variance, dividing by the n. There's a problem here in that we have to estimate two variances, and estimating two variances on small sample sizes is really not a real stable thing to do. So if you have a small sample size and you take what you've got to estimate one variance and then do the same for the other, I mean you're splitting your data pretty thinly. Now suppose we knew that these two variances were in fact the same. Now if they were the same, what we could do is to pool all of our data then and have just one estimate of the variance. And once you get that one estimate, you drop it in both places. And intuitively that ought to be a more stable approach. So let's pool all our observations, get one nice stable estimate of the variance, and do that. All right, so that's the idea of the equal variance assumed row. So if you're going to assume equal variances, what you can do is get one grand or pooled estimate. So pooled meaning you're going to pool all your data together. And here's the formula for that. So if x's are the measures of one sample, y's are measures of the other, what we're going to do is take all these squared deviations, x from its mean, add to that all the squared deviations of y from its mean. So this numerator is just giving you the sum of all squared deviations from the respective means. Now what we're going to do is to divide that by the sample size minus 2, since we've got two means now. So this is going to be kind of an overall average squared deviation from the mean. Now usually in the problems you're given S1 squared and S2 squared, and we remember, I'll just refresh your memory what S1 and S2 squared are. So S squared is 1 over n minus 1 therefore, if I want to know what the sum of those deviations is, we're just going to take n minus 1 times s squared. So that's what's going on in this formula right here. We're taking n minus 1 times s squared. That gives us the sum of those squared deviations. It's probably worth a minute to kind of explain what I mean by equal variances. And I think the easiest way to do that is with some box plots. So let's say we've got a treatment group. Here we have the control group, and we have our dependent variable here, whatever that is. And now, let's say that the box plots look like this. So if the box plots look like this, what you see is that the treatment group has a systematically lower median than the control group, yet the lengths of the boxes are about the same. So in this case, we would say sigma 1 squared is about the same as sigma 2 squared. So we would assume equal variances. There's a fancy name for equal variance that you're going to learn next quarter, and it will be with you for a long time. When you have equal variances, it's called homoscedasticity. So in Greek, the prefix homo means the same. Scedastic means spread, so equal spread. Now let me draw you a picture of the opposite situation. Suppose the box plots now looked like this. So group 1 was like that, and then group 2 had a box plot that looked like this. So clearly, sigma 1 squared in this case is a whole lot less than sigma 2 squared, and you would not be able to make that assumption. So you'd have to go back and use that other equal variance not assumed formula. The term that you will learn about next quarter is heteroscedasticity. So heteroscedasticity is when the variances are not the same. Well, let's go back to the engagement problem. Let's go drop the numbers in. We can find a revised grand estimate of the variance. Now, if you remember what I said we were going to do, we're going to assume that the variances are equal, compute one pooled estimate and drop it in both places, and you'll see that's exactly what we do. We're going to drop that number in both for the highs as well as the lows. In contrast, last time around we put in the separate variance estimates. Right, now you get a slightly different number for the standard error of the difference, 0.049, and if we use this number instead, you get a slightly different z-statistic, a little bit bigger. So you'll notice those two numbers now show up in this row. So here's that t-statistic. This is the standard error of the difference, and the p-value is unchanged really since you're so far out in the tail. All right, so in general, you want to you'd like to be able to use the assume equal variances when you've got small samples. Otherwise, you're kind of stuck using the other one. So here's the general procedure for testing the equality of two means. State your null and alternative. You want to look at your data. Now, when you're looking at the data, you definitely want to look for outliers and right skewness. Those are definitely problems. I'd recommend making box plots like I was drawing. That's a really good way for looking at such data. And then you want normality, especially if you've got smaller sample sizes. Once you've done that and you've convinced yourself that it's a reasonable thing to do the test, then go find the p-value with your favorite stats package. If you've got large samples, just use the unequal variance row And if you've got small samples, you need to make the decision of whether you can plausibly assume the variances are the same. So you're going to get a p-value one way or the other. If that p-value is less than alpha, you reject H0. All right, at this point, you should go watch some of the videos that will do some additional problems.